Hello all, welcome back to our lectures. Today we will be talking about aldehydes and ketones still, but our focus will be on the physical and chemical properties. So today our lecture will be on the physical properties of aldehydes and ketones. In the previous class we introduced the aldehydes and the ketone class, and we talked about their nomenclature. Let us take it off from here immediately. As usual, it's customary. I have a beautiful quote for you. In this quote is from Sonia Sotomayor. Sonia Sotomayor is the first Latinx to be appointed in the Supreme Court. She was appointed by the Obama regime, and she has this to say to us. She says, "Success is its own reward, but failure is a great teacher too, and not to be feared." That is a wonderful motivation. Yes, most times we want success, we want reward, but we are afraid of failure. But she's telling us today that even when you fail, that failure is a great teacher and shouldn't be feared. And by the time you fail, you're going to learn to do better the next time. Let us immediately get into our lectures. Our two learning objectives today is: number one, we're going to demonstrate and illustrate the physical properties of aldehydes and ketones. Remember, the lecture basically is focusing on the physical properties of aldehydes and ketones. And two, we're going to now look at the uses of some important aldehydes or ketones, including some of them that we see in the biological environment. We're going to see this as we move on. Now, physical properties of aldehyde and ketone. You see, now the carbonic carbon, remember, we've introduced these to be the carbonic carbon. The carbonic carbon is carbon that is double bonded to oxygen, and then single bonded to either carbon, and then it can be either to hydrogen if they are aldehyde, or ketone. So now the carbonic carbon is polar. Again, don't forget, this is a polar. This carbon to oxygen bond is a polar bond because oxygen has, remember, oxygen has electronegativity of 3.5. Then carbon has that of 2.5. And by the time you do 3.5 minus 2.5, that gives you 1. And 1 is in the vicinity of polar. So this bond is very polar. But interestingly, it lacks hydrogen. So the lack of hydrogen on this carbonyl oxygen prevents aldehydes and ketones from forming hydrogen bond in their pure state. That is exactly my first statement. So the lack of hydrogen on the oxygen of the aldehydes and ketones prevents them from forming hydrogen bond with themselves in their pure state. In their pure state, they cannot hydrogen bond. However, they can form dipole-dipole with themselves because this is still a polar bond. Now, what is the consequence? The consequence of that lack of hydrogen results to what? Lower boiling point. So the boiling point of aldehydes and ketones are lower than those of the alcohols. Remember, the alcohol has hydrogen and that oxygen, making them to hydrogen bond in their pure state. In this case, they cannot hydrogen bond. So the highest intermolecular force they have is the dipole-dipole. The dipole-dipole. And remember, the dipole-dipole is weaker than what? The hydrogen bond. And as a result, their boiling point are lower than those of comparable alcohol of molecular weight. However, they are higher than those of the alkanes due to polarity. Remember, the hydrocarbons, the alkanes, the alkenes, and the alkynes are non-polar at all. They are all non-polar. They only have the London dispersion force. So let's see what's happening here. Now, if you look at this now, this is the aldehyde. There is no hydrogen here. Of course, again, this is a polar bond. This is also a polar bond that can form dipole. However, there's no hydrogen here, and therefore they cannot in any way hydrogen bond with themselves or form hydrogen bond in pure state. Now, of course, I already said this in the previous slide. The carbon and oxygen exhibit dipole-dipole interaction. and they can form hydrogen bonds with water. Remember we said in their pure state within themselves they cannot hydrogen bond. However, when they come in contact with water, they can form hydrogen bond. And the formation of this hydrogen bond results in water-soluble nature of aldehydes and ketones that have low molecular weight. The low molecular weight, because they can hydrogen bond, they are very soluble in water. Now let's see what is happening here. Now this is an aldehyde. Aldehyde can hydrogen bond because water itself has this hydrogen, so it can hydrogen bond. This is the hydrogen bond that it is forming with water. Remember, hydrogen bond are shown with the dotted line. This is the hydrogen bond. The same thing here with ketone, it can hydrogen bond. So making those smaller ones like methanol itself is methanol and ethanol, which this one contain 1 carbon, 2 carbons. Both of these guys are soluble in water. And when we come here, we find that acetone, which is the first member, or you can call it 2-propanone or propanone even, is soluble in water because they have low molecular weight and they can hydrogen bond water, so they are actually very soluble in water. Now we go to the next one. Now we now take our first reflection problem. In the first reflection problem, what are we talking about? Now it says we draw the structures of butanol, butane, 1-propanol, and propanol. Again, it says all of them have similar molecular weight. All of them have similar molecular weight. Now let's draw it. Now this question is going to lead us to the second reflection question, the continuation, to see what is going on. But first, let's draw them. Remember, butane is an alkane. I'm going to draw them and I'm going to list out the possible types of intermolecular forces that we have. Of course, butane is 4 carbons. Of course, we remember that butane has 4 carbons, so it's going to, and completely saturated because it's an alkane. One, two, three, four. So this is butane. So I've drawn my butane, and of course the molecular weight of butane, if you check the molecular weight or molecular mass of butane will give you 58.12 grams per mole. Remember, we're told that all of them, if you're going to be comparing physical properties, it's good to compare them with those that have similar or approximately the same molecular weight. Now, because it is only London dispersion force that exist here, only London dispersion. These carbon to hydrogen bonds are highly nonpolar. Here it's only London. I'm going to use green. So the only IMF here it has will be dispersion. Let me just write dispersion. I can write London dispersion, it doesn't matter. For now, let me write dispersion. Or short form, I can say London dispersion force. I can use any of them, just to let you know. Then the second one, 1-propanol. 1-propanol is a primary alcohol. So 1-propanol, okay, I can just draw a line. 1-propanol, prop means 3. So I'm going to say the OH group is in carbon number 1. I'll put it here. This is 1-propanol. So this is 1-propanol. Again, remember this is in carbon number 1, the OH group. And the molecular weight of 1-propanol is about 60 point, you see it's very close, 10 grams per mole. And again, remember this is OH group. Anytime you see OH group in a molecule, that molecule can hydrogen bond with itself in a pure state. So the type of intermolecular force that will exist here will be, it's going to have hydrogen bonding, which will be the highest one. And then hydrogen bond is a type of dipole-dipole interaction. And remember, every molecule must have London dispersion force. So this will have the 3 types of intermolecular force. And if this one has 1, this one has 3, that will tell you that this is higher than this one. And then let's go to the last one. In the last one, it's a propanone. Propanone means it has 3. And of course, remember again, you can also say it is 2-propanone. I tell students it doesn't matter. If you call it that, that's okay. Propanone is an aldehyde, is a ketone, sorry. It's a ketone. And as a ketone, this must be in the middle. And the only one position this can be is in carbon number 2. So what are you going to do? You're going to saturate the rest of this. And now we have this our propanone or 2-propanone, whichever you want to call it. Now remember, this doesn't have hydrogen like we just said in the previous slide. So it can undergo dipole-dipole. Okay, wait, let me write the molecular weight. The molecular weight of this is propanone or 2-propanone, it doesn't matter. is going to be, the molecular weight is 58.08 grams per mole. And then what type of intermolecular force? Now this is remember, this is partial positive, partial negative. It's going to form a dipole-dipole itself, and then it will also have London dispersion force, but it can't be hydrogen bond. So that's why I usually list this way, is to tell you that if this one has 3 bonds, this one has 2, this one has 1, it behaves that this is going to be the strongest, followed by this and followed by this. So, but we're going to see this in the next question. Alright, so these are the 3 structures of this, having drawn them and listed the possible types of intermolecular force that will exist in each of them. Now let's now go to the next question. In the next question it says, now this is a continuation of the first reflection question. It says, looking at the structures of butane, 1-propanol and propanone, the ones we've just drawn in the previous slide, and using our knowledge of the intermolecular forces, it says, arrange them in order of boiling point and solubility. Explain your reason. Now, so we're going to arrange it in order of boiling point. Remember, let's go back to that slide. I told you, boiling point increases as the strength of the intermolecular force increases. Remember that the boiling point, BP, that's BP, increases as the strength of the IMF increases. So now let's go back to that slide. If you look at this slide, the one that will be the strongest is the one that has the 3 forces, including hydrogen bond, which is the strongest in all of them. This one has dipole-dipole, and this one has only London dispersion force. Remember, hydrogen bond is the strongest, followed by dipole-dipole and this. So we're going to arrange it from lowest to the highest in increasing order. So this is going to be the weakest, butane. So we'll go back there. So here, butane will be the least, is less than, followed by propanone will be the one in the middle, because propanone has, remember, butane only has the dispersion force, or London dispersion force, LDF, followed by propanone. Propanone has dipole-dipole, propanone, and propanone is less than alcohol, which has all the forces including hydrogen bond, 1-propanol. This is the order. Butane is the least in boiling point, followed by propanone, and the highest is 1-propanol. Now this same, if we go to solubility, remember, intermolecular force is proportional or much closely directly related to solubility, because hydrogen bonding is the most polar bond, and the most polar bond is going to want to interact with water, because water itself is very polar. So this same trend will happen here. So you see, it's going to be butane. Again, solubility will increase with intermolecular force. So butane will still be the least, because it cannot even dissolve in water. It's very insoluble in water. No polar at all. Followed by propanone. Remember, I told you propanone can hydrogen bond with water. I said it already when we talked about when we introduced these physical properties. It can form hydrogen. It cannot hydrogen bond itself in pure state, but it can form hydrogen bond with water. And because it can form hydrogen bond in water, it is soluble. However, 1-propanol is more soluble than the rest of them because of the OH group. So I've already said this in explanation. So to explain it, number one, what are the explanation? Number one, butane only has the London dispersion force. So butane has LDF and non-polar. Butane has the LDF and it is non-polar. Because it's non-polar, it will be the least, it will have the least what? Boiling point and solubility in water. That makes sense. Now, the next one we need to consider is propanol. 1-propanol is the highest one, because it can, 1-propanol can both do what? Can form hydrogen bond with itself in pure state, hydrogen bond in pure state and with water, and hence has highest boiling point and solubility in water. Whereas propanol itself cannot form hydrogen bond with itself. So the boiling point, the boiling point is in the middle. However, it can hydrogen bond with water and its solubility is greater than that of butane. So this is how you explain this in your word, depending on how you want to put it. Let's go to the next thing. Now let's go to the next reflection question. It says, using dotted lines, we should illustrate hydrogen bonding with molecules below. It says use at least 2 molecules. You always see me say this, 2 molecules of water. And remember, hydrogen bond is illustrated by dotted lines. So I want you to form that hydrogen bond between water and this. This is actually an aldehyde. Okay? Of course, this is your cyclobutane. Yeah. So we want to, this is your cyclobutane. If you put an aldehyde here now, so it's going to be, you found out that this is an aldehyde now connected to a cyclobutane. So we want to know how this will hydrogen bond. Remember, it can form hydrogen bond with water. So what we're going to illustrate is that what? Hydrogen bonding. So what are we going to do? Let's see. So I'm going to first of all draw this. Draw the aldehyde itself. And then I'm going to start drawing what? I'm going to use a different color. Let me use blue to put my hydrogen bond with water. So I'm going to, remember this is carbon. Okay, let me use the green. This is partial positive, this is partial negative. So here the negative will interact with the hydrogen. So it's going to interact with the hydrogen because hydrogen itself is positive of the water. So this is hydrogen is partial positive, this is partial negative, partial positive. And again, not done. I say use at least 2. That's what I say. Use at least 2 molecules of water. Remember again, this point is partial positive, so the oxygen can interact with this one. I can make it to go this side. Well, let me use my color. Oh, okay, I can push it this way too. So let me make it to go this way. So I'm gonna put it here. Oh, I was supposed to use the blue. Why am I forgetting that? Okay. All right. I go to use the blue that I used to be consistent. So it's gonna be the oxygen. This will interact with oxygen. So oxygen is O, and then again remember this is partial negative, partial positive, partial positive. So you see the partial positive interacting with the partial negative interacting with the partial positive side of water. So those dotted lines represent the hydrogen bond. This is also hydrogen bond. This is how you do this problem. Okay, we now go to the second part of the lecture, which is the second objectives, to see or highlight some important uses of some common aldehydes or ketones. So important aldehydes or ketones and their uses. The first thing we're going to be talking about is formaldehyde. Formaldehyde or methanol is the first member of the aldehyde group. It is the simplest aldehyde and it's gas at room temperature. Now, it is most commonly supplied in the form of formalin. Formalin is 37% of aqueous solution. We call it formalin. Formalin is used to kill microorganisms and also used to sterilize surgical equipment. And also, it is commonly used in gray anatomy labs, where it is used as an embalming fluid, like in funeral companies, and in cadaver labs. Cadaver labs is where you keep the human remains used for anatomy students to study different parts of the body. So it is an embalming fluid. It can preserve the cadaver as long as possible for students to use in studying. All right, particularly for medical students and those doing biology related classes too. All right, so it's a key industrial chemical in the production of plastics such as formica and bakelite. And of course, this is the structure. Remember, I told you it has mate, means 1 carbon, and is an aldehyde. This is an aldehyde functional group and it has hydrogen to the other side. This is methanol of formaldehyde. And again, you have to memorize the structure. You have to memorize the old name as well, because the old name can come up in exam. Alright, the next thing, other important ones we need to look at are the acetone. Is an important acetone or propanone or 2-propanone is an important organic solvent since it dissolves most organic compound and is also soluble in water. Now it is very small, it can hydrogen bond with water, is soluble, and is also very soluble in most organic solvents. So it's used as an important organic solvent and is also widely used as solvent for coatings. Vanillin is found in vanilla bean and is used for vanilla flavoring. Cinnamaldehyde is found in the oil of cinnamon and is used for cinnamon flavoring in food as well and snacks. Menthone is another important one that is found in the menthol plant. Found in the mint plant rather. Menthone is found in the mint plant and used in peppermint flavoring. The common peppermint flavoring you get in candies and even used in cooking as well is menthone is an aldehyde, and you got that from the mint plant as well. Now, other important ones we're going to look at, particularly those of them that have some biological connotations. Carbonyl functional group can also be found in biological compound. Common biological compound we will see here is a progesterone, testosterone, which are the male and female sex hormones that are produced in the gonads, and aldosterone. So the progesterone, of course, is a female sex hormone. This is a female sex hormone. Female sex hormone. It is produced in the ovary. And of course, we look at it, this is a ketone. This is a ketone functional group as well. Those are ketone functional groups. The testosterone also is a male sex hormone. The male sex hormone. The male sex hormone is produced at the testes. I think no, that's not the spelling of the test. I think the test, yeah, I think it's this. If I'm not getting it wrong. Now the testes, of course, is produced at the testes, and again, if you look at it, it has this here. So this is an aldehyde as well. Oh, it has an alcohol. This is an alcohol. We're not talking about it now, but this is to tell you that it's well focusing on those of them that have the aldehydes and ketone. And again, we have the aldosterone. The aldosterone again has a couple of them. The aldosterone has one here. You see, both of the three of them have the ketone group at this point in this fused ring structure. Now, of course, all these guys are all derived from cholesterol. This is the cholesterol nucleus. So, but this is not what we're going to be talking about now. But most of these guys they're all steroid hormone because they're produced. That's why you see them end by sterone. They're all from cholesterol. So these fused rings are all is what we call the steroid nucleus. Anyways, that is not what we're focusing. We're focusing on those aldehyde and ketone functional group. Again, look at this here. This is, there's a hydrogen here. So if there's a hydrogen here, this is what an aldehyde functional group, and then this is also a ketone functional group. So all these molecules are biological aldehydes and ketones. So now aldosterone is a mineralocorticoid. It's a mineralocorticoid. Now it is a steroid hormone that regulates the water and salt balance in the body. It is produced in the adrenal cortex. It is produced in the adrenal cortex, where it responds to changes in both electrolyte and water balance in the body. That is exactly what it does. Now, the last but not the least of some other important aldehydes and ketones we're going to be talking about are the monosaccharides, the common monosaccharides, the glucose, the fructose, and the galactose. The glucose itself, look at it. The glucose here, in carbon number 1, it has the aldehyde functional group. This is the aldehyde functional group. Now, you see the fructose itself is a ketone. Look at it. It has the ketone functional group here. Whereas the galactose here has the what? Still has the aldehyde functional group. Of course, The importance of this monosaccharide is that they are the simplest carbohydrate breakdown during digestion, and they play an important role in the production of energy in metabolism. Remember, the first point of metabolic breakdown of glucose after digestion is glycolysis, where glucose is broken down to produce energy. Now, these other molecules are also broken down through those pathway to release energy. And like I said, there are a variety of these aldehydes and ketone compounds, both in biological and non-biological systems. And having said that, we've come to the end of this lecture. Thank you for listening. Bye.